Hello, everybody. Thank you for your patience. It's a great pleasure for me to introduce you to this series of webinar within the frame of the project ANML. ANML is a project funded by the European Innovation Council, which is dedicated to making green hydrogen from dirty waters. That includes seawater and wastewater, among other things. We're starting this series of webinars with our coordinator, Pau Farràs. I'm gonna introduce him in just a minute. But before we do that, just a kind reminder that we plan on hosting a long series of webinars within the Animal Framework. So please subscribe to our newsletter, subscribe to our social media channels, and keep in touch with us to learn more about direct seawater electrolysis, about our project, and about the European Innovation Council, which is our main funder in this project. For me, it's a pleasure to introduce our speaker today, Professor Pau Farràs from the University of Galway. I know Pau since a long time ago. I think we first met in person in a young chemistry conference in Barcelona, or maybe the one before that in Zaragoza in Spain, maybe 10 or 15 years ago. Pau is an amazing chemist. He's always been super passionate about sustainability and making the most of the energy we get from the sun. He's running his own group in the University of Galway in Ireland, doing photochemistry and chemistry with light. And he's worked in many very prestigious universities like ICIQ in Spain, ICMAB in Barcelona, DTU in Denmark, and then Newcastle University in the UK before moving to Ireland, where he established his own group and basically runs a bunch of European grants. I think at the moment there's 6 going on, one of which is ANML, a project that he coordinates from Galway, and where us from Agatha Communications take care of the communication and dissemination, and hence this series of webinars. So Pau, welcome to our webinar platform. It's very nice to see you here. How's everything? I know you're a little bit jet lagged from a trip to a Gordon conference, but hopefully you're all ready to present today.
Yes. Good morning, everybody. Definitely, I will go for several coffees after we finish with the webinar to stay awake for the day. But it is very nice to be starting this webinar series in NML. And thank you for the presentation, Fernando. Indeed, it's been many years since we have known each other.
Yeah, so just before we start, I'm just gonna leave the floor to you, Paul, because you're the main person in this webinar. We're really looking forward to hearing about ANML and direct seawater electrolysis, the challenges and opportunities of this technology. But before we do start, just a kind reminder to everybody watching that this is streamed on YouTube, so there's not going to be an interactive Q&A at the end like you would maybe have on Zoom. However, we do have the opportunity to ask questions to Pau Farràs. So maybe just use the chat for that. We're monitoring that, and we'll have some time for Q&A after the presentation. And without further ado, just warm round of applause virtually to Pau Farràs. Pau, the floor is yours.
Thank you, Fernando. So good morning, everybody. And it is again a pleasure to have to be presenting this first webinar on the challenges and opportunities on impure water electrolysis for hydrogen production. Since this is the first webinar of the series, I thought that it was good to start with the broader general topic about green hydrogen production, and then deep into what we have been doing a little bit on NML, and then we'll lead basically for the other webinar series to some of the other partners from NML to go much deeper into the technology that we are developing. So just to kickstart, the outline of today's presentation will be based on these 4 main topics. So we will start first with some aspects about green hydrogen production and why hydrogen, why now. Then why do we need, or why do we bother for seawater electrolysis or impure water electrolysis, as we like to call it. And then we'll go into some detail about the NML project that I'm leading and that we have been working on for just over a year. And then we'll finish up with some conclusions of what I see as some of the challenges and opportunities for impure water electrolysis. So going directly to the green hydrogen production, but first of all, I think that it's important to mention that why do we need hydrogen? And the problem is that if we want to go away from fossil fuels and go into using renewable energies, one of the major issues that we have on renewable energies is that they are intermittent, in particular when we talk about solar or wind. Of course, the advantage is that there are no CO2 emissions, but this intermittency that you have for renewable energies means that you need to have some way of storing the energy so that basically when the sun is not shining and the wind is not blowing, we could have a fuel that is stored that we can use it. And in some cases, batteries can be taking this part of the job, but not in every single case. So one of the issues of why do we need storage is related to what we call curtailment. So curtailment is when you have an excess of energy that you cannot use because either there is not enough demand or because the electricity grid is not good enough to basically cope with the amount of renewable energy that you have. And here in this plot from the Fraunhofer Institute, what is shown is that in Europe, for example, if you have a system that is not integrated, that basically you have renewable energies installed all over the place without any integration and storage, the level of curtailment is in the order of close to 50 terawatt hour. Okay, so that's an amazing loss of energy that otherwise it is expensive, and therefore it is a loss of a lot of money. Instead, if you have integration within the energy system and also including storage solutions, like in the case of hydrogen, for example, then the level of curtailment is reduced significantly. And that's why hydrogen can play a significant role. So if you see here from the roadmap from the fuel cells and hydrogen joint undertaking form several years ago, the targets that they had for 2030 and 2050 were based on the fact that by 2030 there was supposed to be this 40% CO2 reduction and about 27% of renewable energies with 27% of energy efficiency. This has been increased now with the newest regulations from the European Commission, but the target for 2050 really stands. So this 80 to 95% of CO2 reduction that we require at the European continent is still there, since we need to have this CO2 neutral continent by that time. And that's where hydrogen plays a significant role, since basically hydrogen can be used as an energy carrier, a clean energy carrier that doesn't contain any carbon. It can be used in the transport and the energy applications. It can be used to generate electricity or heat. And there are different situations and that basically you can use hydrogen and will be on a case-by-case scenario that they become useful or less useful. So this is some examples of different systems. So we have the power generation, transportation, and heating, for example. And one of the important aspects to remember is that if we want to keep the CO2 emissions by 2050, there is a significant gap that needs to be filled with storage solutions like hydrogen, for example. And this is where mission innovation challenges come into place. And in the last list that was published some months ago, we see here that one of the innovation challenges is number 8, which deals with renewable and clean hydrogen innovation, which is led by Australia, the European Union, and Germany, with the participation of several other countries in the world. So that's like a testament that green hydrogen is going to be in the equation, is going to be in the energy mix at the global level to cope with this increasing level of renewable energies that we require. And of course, this cross-coupling that I'm sure that you have learned about, where if you have this large-scale integration of renewable energies, you need to have this buffer storage. and then use this fuel like hydrogen or some other derivatives that you can use from green hydrogen to basically decarbonize these four different end uses. So decarbonize the transport, decarbonize the industry, decarbonize the heating and power, and also to be used as a feedstock using, for example, capture carbon to produce carbon liquid-based fuels, or even to produce ammonia for fertilizers as well. Yeah. So as you can see, there are different roles that hydrogen can have as an energy vector that makes it very attractive for the next couple of decades, where increasing amount of renewables will be put into place. And that's why it is now the time that it is important to start looking at hydrogen as the solution. Another example is, for example, in the transport. And the question is, what brings hydrogen into the game of transport? This is kind of a cartoon representing the comparison between what would happen in the case of a hydrogen filling station or in the case of a battery storage or a charging station using batteries for transport. One of the things that is important to realize is that the way that hydrogen is filled, it is very compatible, very equivalent to what we are used to with gasoline and diesel. And of course, it's much faster than in the case of the fast chargers. This is just an example, but as you have seen probably in the news, there are also new developments in battery technologies that allow for also fast charging, and that will probably could outcompete the use of hydrogen for small vehicles, but not for larger vehicles. Another example is not only on the charging time of your of the vehicles, but also on the infrastructure that is required. So if you look here, for example, what would be required for charging about 60 cars? If you compare the size and the power that is required using a hydrogen refilling station or a fast charger for small and larger vehicles like trucks or buses, you can see here that there is a requirement for a huge amount of energy that needs to be put into the place for the fast charging, which of course becomes a cost to the electricity providers and the electricity grid. And this can be minimized quite significantly while using hydrogen. Okay, so in the case of hydrogen refilling stations, the hydrogen can be stored on site and then delivered in a much faster and smaller energy requirements and cost requirements compared to a fast charging station that would meet the same amount of vehicles. So the hydrogen economy, as I said, is important as a sector coupling. And in the last 10 years, there has been a significant boom that basically is the why now is because the increasing amount of renewable energies that we will have on the energy mix of the different countries. And this has led to a boom again into hydrogen and the appearance of different levels of end uses for hydrogen, in particular for the transport, where you can see examples of fuel cell electric cars like Toyota or Hyundai or BMW. The fact that we can see a lot of hydrogen buses already running in many cities in Europe. We have a couple of examples of hydrogen trucks as well. And in places where it is even more interesting is in this long distance transport, like for example in trains, and that's a train in Alstoms in Germany that is being powered by hydrogen and is in operation for over 2 years. And also examples of hydrogen ferries, like in the case of San Francisco, or for example in Norway, there are a couple of hydrogen ferries as well that are in operation. Okay, so as you can see here, that's another study that provides some extra incentives for using hydrogen for buses and trains. And that's an example of a study done by Sintef on a single light train that is running in Norway. And you can see that the cost of running the train using hydrogen, it becomes much more competitive already compared to diesel or using the electric wires that we are used to for trains. Okay, so these are a couple of examples that showcase that hydrogen becomes a very important energy vector for the energy mix. And this has been also identified by the European Commission and by the roadmap done by Hydrogen Europe, which not only in terms of the benefits of reaching the climate targets for the CO2 reduction, there is also a significant interest for the economic value that you have on the hydrogen supply chain, and also the reduction of other gases, not only CO2, but for example, of the nitric oxide from local transport to basically improve the quality of the air in our cities as well. And finally, of course, important to realize that there is a huge amount of skills and jobs that will be created based on the hydrogen supply chain that needs to meet the demand for this energy vector as well. So another kind of extra incentive that appeared late last year was basically coming from the European Commission again, where it was demanded that green hydrogen had to be included as part of industry and transport in a level that basically 42% of the green hydrogen has to be included in the industry energy mix. And also that by 2030, there will be a requirement of about 1% of green hydrogen transported into transport fuel. For example, and this is particularly related to the use of sustainable aviation fuel that would require also green hydrogen for that purpose. Okay, so if you look at these numbers, this will mean about an extra 4 million tons of green hydrogen per year. That is the demand that this creates by 2030. And this equals more or less about 30 gigawatt of installed electrolysis. And that's orders of magnitude higher than the electrolysers installed currently in Europe. Okay, so when we talk about green hydrogen, it's not only electrolysis that we can use to produce green hydrogen. There are other ways to produce green hydrogen. So of course, if you look at the natural resources, you have the steam methane reforming. That's the main source of hydrogen, like over 95% of the hydrogen that we are using at the moment is coming from this process that is based on fossil fuels. And therefore, all this hydrogen needs to be replaced by green methods. It can be done by electrolysis, by directly electrolysers or photoelectrolysers or photocatalytic reactors, but it can be done also, for example, on biomass reforming or waste reforming that can lead to the production of green hydrogen. And some of these technologies is what we actually have been looking at for this hydrogen portfolio project from the European Innovation Council that you can find information on our website that links to the portfolio of 9 projects that are working on these different technologies for green hydrogen production. So another important aspect to realize is that it is already available, and you can find, for example, in this picture, it is something that you can find in eBay, for example, that you can buy a small electrolyzer for a decent price. The problem is that when you try to scale the production of these electrolysers, then it's becoming more challenging. In some instances, you can have, for example, this system that is a containerized PEM electrolyzer, 1 megawatt, that is available in the Orkney Islands in Scotland, next to the sea. So there are some systems that are, of course, commercially available and at different sizes, including, for example, this 10 megawatt PEM electrolyzer that is available in the Shell refinery. And that's currently one of the largest electrolysis systems in Europe at the moment. Okay? So you can see that this increasing demand of green hydrogen is being translated into new technologies, new ways of producing hydrogen to meet those demands as well. And so then is why we want to see what happens when we use impure water, or in the extreme case of seawater. And the question is, why do we need to look into this? Okay, because for example, in some of the systems that I have shown you before with the PEM electrolyzers, the water that is used in those systems is just deionized water. And therefore we need to see what is the reason why we want to get rid of, or be able to use other sources of water to produce green hydrogen. If we look a bit into detail about the amount of water that is required to produce hydrogen, we can see in this study that it is actually very minimal. Okay, so if we see here what is the water consumption by application, and we look at the amount of hydrogen that is produced today, the dot is almost invisible. Okay, so you cannot see, because the amount of hydrogen that the amount of water that is required for hydrogen is rather small. Okay, so you can see here in those numbers that is less than 1 liter per kilowatt hour of hydrogen equivalent that you need for water electrolysis. If you compare those numbers, for example, of the agriculture or the municipal water consumption, that's orders of magnitude higher. And even when you look at the expected levels of green hydrogen production reached by 2050, this value is still very much similar to the desalination that was available 5 years ago, right? Okay, so the question is, why do we bother? And another important aspect is to realize that the cost and the energy required for water purification for electrolysis is about 1% of the total cost, yeah, in general. But I'll show you a couple of examples that have updated some of these numbers to be a bit more realistic on what is the cost and the consequences of using this purification step. But before that, just want to give another number with linking the desalination and the hydrogen production. So for example, in this picture, you can see the largest desalination plant that is in Abu Dhabi, the Jebel Ali, which is able to produce over 2 million cubic meters of water per day. Okay, so if we translate this amount of water into amount of hydrogen that you can produce, this will be similar to about 200,000 tons of hydrogen per day, or the equivalent of about 460 gigawatt of electrolysis. Okay, so as you can see, this number is already 1 order of magnitude higher than the target for the European countries by 2030. Okay, so if all the water that is coming from a desalination plant was to be used for hydrogen production, this will meet the electrolysis requirements at the global level for the targets for 2050 already. Yeah? So as you can see, there is not much of a initial interest of why do we need to bother of using not impure water. But if you look at actually some of the places where water is available, and as you can see, for example, the wind resource in Europe, it showcases here that most of the best winds are happening on the ocean, as you'd expect. Okay, so if you want to use renewable energy to drive the production of green hydrogen, you will need to go for places where it is on the coast or offshore platforms, and that's what several companies, including Siemens or ERM, have been looking at in the last few years, where they are looking at installing platforms offshore with wind turbines and electrolysers already on board. And therefore, the only source of water that you would have there is seawater. Yeah. So there has been a couple of different analyses in the last few years about why do we need this direct route for direct seawater electrolysis versus the conventional water purification and the conventional electrolysers. But even though, because of the reasons that I was showing you before, the amount of papers that have been published in the last few years on direct seawater electrolysis have increased exponentially. Okay? And that's something that is worth noting. Another important aspect to consider was covered by Becker et al. Last year in this review paper in Sustainable Energy and Fuels about the ways important to look at impure water electrolysis. Okay, and here it is important to note that in the EU, the Joint Research Center for guidelines for water testing in water electrolysis, they mentioned that you need water quality of less than 1 microsiemens per square centimeter per centimeter. So this means that you need really DI water to produce hydrogen using the traditional water electrolyzers that we have now. And with recent costing of the level of water purification that you require for a PEM electrolyzer of about 1 megawatt system, you can see that about 22% of the total balance of plant for the cost of this system stack is coming actually from deionized water purification. And it is important to note that it is insensitive to the system size and also the annual production rate of hydrogen. Okay, so there are different reasons why it is important to try to reduce the requirements for water quality in water electrolysis so that you can reduce the cost, but also avoid competition of water that is used for drinking water versus water that is used for hydrogen and fuel production. And in this scheme that was published in that review paper last year, it shows a couple of the challenges that you have when using impure water, where you have organics, you have metal salts, you have anions that can interact with the electrocatalyst, with the membranes, leading to different unwanted reactions that you need to avoid if you want to use that. And of course, another important aspect is that when you have a system with a water electrolyzer that contains pipings that have different metals, these metals can actually dissolve into the water into the electrolyte and go into the system, into the stack. And therefore, these contaminants can affect the performance and the stability of the system if it's not properly studied. Okay, so that's why we believe that it's important to understand which are the streams and which are the conditions where a stack system, a water electrolyzer system, can withstand different variations in the composition of the electrolyte. And of course, in our case, most interested in the seawater. Okay, so in terms of some of the challenges that we have in seawater, if we compare the four main technologies for water electrolysis that are available at the moment, this would be the alkaline water electrolysis, the anion exchange membrane electrolyzers, the proton exchange membrane electrolyzers, and the high temperature electrolysis. If you look at these systems, and we see which is the main challenge when we are trying to use seawater as your source of water, we realize that, of course, in seawater, the major component that you have is sodium chloride. Okay, and when you have chlorides in solution, then you have a direct competition on the anodic side between the water oxidation reaction and the chloride oxidation reactions. And these chloride oxidation reactions are pH dependent. You can oxidize the chloride to chlorine, to hypochlorite or hypochlorite. And because it is pH dependent, there are places, there is a pH range where there is a significant overpotential for water oxidation versus the competing chloride oxidation reactions. And this is what is known as the alkaline criteria, okay, that basically above 7.5 of the pH, the overpotential, so the thermodynamic potential for water oxidation for OVR is about 480 millivolts, which leads kind of enough room if you have a good catalyst to basically favor the water oxidation versus the chloride oxidation. And in the literature, there are a couple of examples where you can see that this or potential of low less than 480 millivolts has been achieved for several systems, including the iridium oxide or the nickel iron catalyst, manganese catalyst, and iron catalyst. Oh, in all of them, you can see that the upper potential is lower than 480 millivolts, and this means that then the chloride oxidation shouldn't happen because it's not thermodynamically favorable. One of the issues that we have here in this plot is that these overpotentials are measured actually at very low current densities of 1 and 10 milliamperes per centimeter. And these are not industrially relevant current densities. Okay, so you need to go to 50 to 100 times more compared to these numbers. And therefore, if you increase the current density, the overpotential will increase, and therefore you will have the competing reaction of chloride oxidation with water oxidation at the same place. And if you have chloride oxidation, you are creating a very corrosive environment for the different components that you have in the stack. And this can lead to degradation of the electrocatalyst, degradation of the membrane, and degradation of the different components like the bipolar plates or even the hardware of the electrolyzer that gets corroded, could get corroded very easily. So some of the challenges that we see are, for example, in the case of the hydrogen evolution site, you have the presence of some of the cations that are there in trace quantities in some cases in seawater. And under the reductive conditions that you have in the AGR, in the cathode side, these cations can deposit on the surface and they can passivate completely the reaction of proton reduction to hydrogen. There is also the inherent corrosion by the presence of the chlorides that can lead to basically dissolution of the cathodes, and therefore you need some sort of a corrosion-resistant layer on top of the cathode to prevent this corrosion. There is also the isolation of the catalyst layer. Okay, so that there is in some instances you could try to envisage protecting layers on top of the anode that kind of prevent the cations and the ions reaching the active sites, and therefore only having water getting into the active sites to have the selectivity that you require for oxygen production. And this can also be applied on the cathode side. Okay, so you can also imagine some sort of these perm-selective layers where you prevent the interaction of the species that you don't want to the active sites on the both on the cathode and the anode. And a couple of papers have appeared in recent months, where, for example, for the anodic side, a layer of chromium oxide has been shown to basically prevent any chloride reaching the surface of the active catalyst. And this kind of helps to achieve the selectivity that you require for avoiding the oxidation of chlorine species. Okay, so this leads to what ANML is about. And ANML, because of those reasons, what we are trying to achieve is to move away from the use of DI water and using basically the fact that basically most of the water that we have on the planet is coming from the oceans, about 97%. And therefore, what we have been proposing to do in this project is to look at 3 different electrolytes of different associated challenges. Traditionally, with anion exchange membrane electrolysis, the conditions that are used are 1 molar KOH. So our initial targets are based on reducing the amount of KOH so that you can reduce also the handling of the corrosive potassium hydroxide that you have in the electrolyte, so that it is less hazardous also when you want to scale up to megawatt scale systems for hydrogen production. Then to avoid completely the use of KOH, we wanted to use this electrolyzer stack using DI water, okay, and that's basically to mimic the performance that is now being used in PEM electrolyzers that are using DI water without any added salts. And then to mimic the conditions of seawater, the last electrolyte that we'll be testing is using 0.5 molar sodium chloride, which is the concentration of salt sodium chloride that you have in seawater. Yep. Of course, this is a simplification of the challenges that you have in seawater, since you don't have any other of the trace ions that you have, for example, the magnesium or the calcium or the bromides that you have in seawater. We are not looking into this for that particular project in animal. Yep. So animal, we started in September 2022. We are in the second year of the project, and we are 11 partners across 9 different countries with a budget of over 5 million euro. And the idea of the project is to look at the different components that are required to build a water electrolyzer stack. Okay, so we have 4 technical work packages that are dedicated to catalyst design and manufacture. And this is the work that is done by the University of Galway, my team here in Galway, EPFL in Switzerland, the Joseph Stefan Institute in Slovenia, and Denora in Italy. Then we have a dedicated work package on the fabrication of the ionomers and the membranes that you require. And that's, of course, as you can imagine, challenging, because the stability of these anion exchange membranes is not very good. So there is a lot of requirements for improving the stability under those conditions, and also making sure that they are compatible with the presence of chloride ions in the solution. And that's the work from all these partners that are working on the membrane and ionomer development. Then these new components that we are developing, they will be integrated into single cell systems to do testing. And we have developed standard electrochemical systems so that we can do the testing under the same conditions in different labs to ensure reproducibility of the results of both the performance and the stability of the catalyst and the membranes. And finally, the last work package is the integration of all these components into a stack of at least 1 kilowatt to produce hydrogen using these electrolyte conditions. All this is also being guided by eco-design and the sustainability impact. So, for example, what we are doing is looking at the impact on the environment of the processes to manufacture the catalyst and the membranes, so that we can reduce the impact that you have from the very beginning, trying to use synthetic methodologies that are compatible with the green chemistry principles. And this is linked to the different work packages on communication, dissemination, and exploitation, and also all these activities that we have with the other 8 projects that were funded under STEM call on green hydrogen production. So the overarching goal of NML is to develop this stack that contains non-precious group metals. Okay, so we don't want a water electrolyzer that contains iridium, platinum, ruthenium, because they are expensive and they are not very abundant. So if we need to scale water electrolysis systems to meet the demand, you need to use abundant elements, and that's why we are looking only at non-precious metals. We want also to use to avoid using fluorinated materials, and that's directly related to the perfluorinated substances ban that it is in discussion at the European Commission now. That affects very much the proton exchange membrane systems, with Nafion being perfluorinated polymer. Okay, so the membranes that we are developing, they don't contain any fluorinated elements. Of course, the major challenge is the compatibility with these impure water sources, and in particular, the use of 0.5 molar sodium chloride as the electrolyte, and the recyclability of the components. Okay, so making sure that whatever we have in the stack can be recycled properly, so that we can build more when the end of lifetime of the system is finished. Yep. So some preliminary results that we have done with NML is that we have been working, and that's work between my team in Galway and a group from Peter Strasser in TU Berlin, where we have developed a PGM-free single cell system containing cobalt oxide, cobalt phosphide cathodes and anode with a commercially available membrane like a Sustanion. This has been done at 1 molar KOH. We are now working on reducing the amount of KOH to get into lower pH and also get into DI water at the end. But in this study, what we can see is that we have been able to reach already the targets of 2 volts of cell potential at least over 1 amp per square centimeter. We have done also stability test at this is 6 hours, but we have also done at 100 hours with minimal degradation of the system, showing that the components that we are developing as part of the project, they are meeting the requirements for an industrial application. In a more general way, we have also been publishing other papers, and that's some work that has been published by the groups in EPFL from Chilejo and from Jan van Herl, and also from TU Berlin with Peter Strasser, where in the case of Chilejo, they have been able to showcase one system that contains an ion exchange ionomers that can sustain for over 100 hours hydrogen production using pure water electrolysis. Okay, so that's using directly DI water in platinum group metal-free electrocatalysts. So no PCMs, and they have been able to showcase that you can get the stability of over 100 hours at the target KPIs. We have been looking at different catalyst materials as well to try to improve the performance of the different components. But all these will be explained in more detail in the next different webinars that we'll be organizing by the different partners, where they will go much more into the technical details about the different components and the cells and the stacks that we are developing. Okay, so just to finish up, that's, for example, one of the systems that EPFL has been working on, where we have now a complete stack of over 1 kilowatt with 5 cells with all the balance of plant, so that we are now in a position to start incorporating the electrocatalysts, the membranes, and the ionomers that we are developing as part of the project into a full stack system, and compare the performance at the different electrolytes that we are working on. And to finish up, I just wanted to showcase a couple of things and why it's not only important to mention seawater as a low TRL project and innovation project, but there are actually many developments globally that showcase the relevance of seawater electrolysis. There's an example of Hyundai in Korea, where they have signed agreements with several research institutions in Korea to develop commercial systems for seawater electrolysis. That's an example in China of Dongfang Electric company that last year they successfully reported the production of hydrogen using the claimed non-designated seawater electrolysis powered by an offshore wind in an offshore platform. And also the fact that there are different small startup companies that they are working on developing products for direct seawater electrolysis as well. Okay, so this is a testament as well that this topic is becoming more and more important to make sure that you can get electrolyzer systems that are stable and that can meet the requirements for large-scale deployment. And with that, I'll just conclude with a couple of points to mention that seawater electrolysis or impure water electrolysis, it is very challenging, as I have tried to show you, where the most important point is to control the selectivity for water oxidation in the presence of different ions. Of course, the main one is chloride, because that's the most present in seawater, but there are other ions that also can affect the selectivity of this anodic reaction. the fact that trace ions can have a huge effect on performance and stability. And there has been several reports in the literature where you have seen that for nickel electrodes, small amounts of iron improve significantly the performance of the catalyst. But for example, from some of the trace ions, it has been shown that the performance can be reduced significantly, and particularly the stability as well. It is very important to develop these new components, the electrocatalysts and the membranes, to ensure longevity of the electrolysers, to meet at least these 80 to 90,000 hours of operation that is required for a cost-effective solution for water electrolysis, and also that the application for offshore locations is very interesting. And that was just a testament of the examples that Hyundai or the company in China that were already testing these systems in offshore platforms. So with that, I'd like to thank my team in Galway, those that are working directly on NML, which is Sohail and Praveen. And also all the partners from NML who have been working very hard to start working on this project and have results within the first year of the project already. And with that, I'm very happy to take any questions from the audience. And I'll just stop here now. Thank you.
Thank you so much, Pau, for a very nice presentation. It's actually good because we do have questions from the audience already. So I'm just gonna start with the one we got. But before that, just a quick reminder to everybody that you're free to submit any questions or any ideas that you have using the live chat on YouTube. So you should see it on the side of your screen or maybe just below the video. Feel free to write it there, and we'll check the questions and pass them on to Pau Farràs. So the first question was related to corrosion, and actually, like I really like it because it was one of the things that I had in mind to ask you too, because you mentioned some figures along the presentation, like the cost of using water purification in electrolysis is up to 22% of the cost of the whole platform, and that's insane. And in that same matter, like a few months ago, I read that the cost of corrosion worldwide is around like 3% of the world's GDP because of all the bad things that corrosion does. And I imagine in environment that has like seawater, a lot of chlorine, a lot of oxidizing materials, that's a challenge. So the question we got is like, what type of corrosion issues can we observe in direct seawater electrolysis, and also what kind of materials can we use to avoid this effect, the effect of corrosion?
That's a very, very critical aspect of using these saline electrolytes. So a very simple example is for alkaline electrolysis or for alkaline media electrolysis, both in water electrolyzers and with the membrane systems. The most typical material that is used for the anodic side is nickel, either nickel foam or nickel mesh or nickel felt. Okay, so one of the challenges that we have observed is that when you use these bare electrodes in these saline conditions, after a couple of hours, the electrode is completely dissolved. Okay, so you cannot even have an electrode that is stable under those conditions if you don't have protecting layers or you use a different type of electrode system. Okay, so for example, one thing that we can learn from is the chloralkali industry. And the chloralkali industry, they have had several decades of experience of working under these saline conditions with the production of base and acid. And the first thing that they realize is that nickel cannot be used in those systems. Okay, so for example, the typical materials that are used are based on titanium because that is resistant to corrosion. So this choice of materials is what is also like guiding us to basically move away from the traditional electro materials that are used in alkaline conditions to make sure that we have these corrosion resistant systems. Another thing that we have been working on is actually use protecting layers on top of these electrodes that are not stable under these conditions, and use these protecting layers as a way to avoid this dissolution that happens because of the corrosion. Okay, so there are different ways that you can try to avoid this corrosiveness environment affecting the performance of the components.
I mean, on that last point that you mentioned, I don't know if you're reading the questions too, but we do have a question about those coatings from one of our colleagues in the green hydrogen portfolio. Just a bit of background on that. You already mentioned the presentation, but basically the portfolio is a set of 9 projects funded under the same call by the European Innovation Council, and we all work together in different aspects of the projects to basically achieve the same goal, which is moving towards the hydrogen economy in Europe and making greener hydrogen. So we got a question from one of our portfolio colleagues in Photosyn H2, which is another project in the portfolio, asking about those materials. What specific materials can we use to insulate, to protect the anode and the cathode in a way that they're less vulnerable to corrosion and other effects? Because I mean, so far we can only work at very high pH, so that also is probably very challenging for the long-term maintenance of the materials and the long-term stability.
Yeah, I mean, in terms of the why we want to move away from this very high alkalinity and try to reduce the amount of potassium hydroxide in the electrolyte is related to the safety of having such amounts of corrosive electrolyte in an industrial environment. And there has been many studies from some of the water electrolyzer companies, like, for example, Siemens or Nel, that they have shown that there is a significant hazard of having these big volumes of potassium hydroxide electrolytes in a system, and this can lead to safety concerns. So that's why we are very interested in moving away from this high alkalinity and getting closer to the DA water, or at least reduce the amount of potassium hydroxide. In terms of which type of protecting layers can you use, I mean, there are hundreds and hundreds of studies and a lot of decades of knowledge in the maritime industry of protecting layers for ships that avoid corrosion in these saline environments. So there are many different ways that you can protect systems and protect metal alloys from corrosion. One thing that there is much less expertise is the combination of the corrosiveness of the saline conditions plus the oxidative power that you have in anodic reaction, because in the sea you don't have high oxidative conditions. And this is the challenge that we have now, because most of the materials that have been used in the maritime industry for these protecting layers and the corrosion, they are not stable under oxidative conditions. But for example, in these last few months that they have, for example, this layer of chromium oxide, it seems to be very good as a anti-corrosive layer that is also stable under oxidative conditions. But there are also other systems. There might be other polymers, for example, that you can use to protect the electrode surface and the catalyst from corrosion as well.
Thank you, Pau. So we do have another question that feels a little bit technical because it's asking about current densities and voltages that we're going to use in the long term. So maybe we can leave that one for the offline discussion, or maybe a follow-up on email. But we did have another question regarding some of your very first slides that showed the map of Europe and the areas that have a lot of access to free, basically, energy from the wind and the sun, and at the same time they have very easy access to seawater, and that's, you know, the Mediterranean coast, the Atlantic coast, and then also the islands like Ireland where you live. So in that sense, I mean, I wanted to ask you a little bit about like which are the most promising zones in Europe to establish establish these like hydrogen production factories and hydrogen generation factories, if they're in land actually, or they are maybe offshore. And then maybe comment a little bit on the concept of the hydrogen valleys, which is a very important concept in the European Union's plan towards carbon neutrality in 2050, and how those valleys could become hubs of producing hydrogen and then storing it, but then also using it in interesting things like maybe making new chemicals. Something that you're also working with in terms of making the most of CO2 and CO2 valorization reactions, which could be combined with the power of hydrogen. I don't know if you have any views on the future of hydrogen valleys, particularly in Ireland, but then also in other zones of Europe.
Yeah, so in terms of the first question, so if you look at the European map, the resources that we have are wind and solar. No, if you look at the solar resource, it is mainly in Spain, Greece, Italy. In most of these places, you might have a lot of solar resource, but then the problem is the water. And in most cases, there is not even seawater available in the places where there is more solar irradiation. Uh, the last thing that you want to do in those places where there is a water shortage is to use river water that you are then competing with the drinking water. And therefore, you need to be very careful also when you are planning large scale deployment of hydrogen production systems where you have the availability of the resources. In terms of wind, that's kind of a bit of a different story because the best wind resources are on the ocean. And they are on the west coast of Ireland, in Scotland, in the west coast of the Netherlands and Denmark. And of course, then the main resource that they have there is seawater. And that's why we believe that having these technologies to be able to minimize the amount of water purification to produce hydrogen plays a significant role. In the case of Ireland, for example, it is expected that the potential on the west coast is of over 40 gigawatt of wind resource available, and this resource can only be transported into Europe by using a fuel. It is not possible to transport all this renewable energy with cables, and therefore that's why hydrogen systems in that context is very important. In terms of the hydrogen valleys, that's a very good strategy to try to kickstart these small ecosystems that you require, where you have not only the production but also the use and the storage. Some examples of hydrogen valleys are, for example, the Green Highland project in the island of Mallorca, where there is hydrogen production using solar, and then this hydrogen is used in different applications. So there are applications on transport using hydrogen for powering buses and cars. There is hydrogen for injection to the gas grid to decarbonize the gas grid. There is also hydrogen for stationary applications. For example, it was recently announced a couple of months ago that one of the hotels in Palma de Mallorca will have the first hydrogen fuel cell as a power source using hydrogen that will be produced using this hydrogen valley concept. So I think that that's a very important aspect that you have to start putting together these small ecosystems so that you are ensuring that all the different components in the supply chain of hydrogen are available. And then the next step, when there is enough of these clusters, would be to start clustering clusters as well. So basically, if you start, for example, in Ireland, we will be starting now Hydrogen Valley in the area of Galway. And then you can imagine that in the south in Cork, there will be another hydrogen valley. And in the east in Dublin, there will be another hydrogen valley. And then if you interconnect the different hydrogen valleys, then basically you have a hydrogen ecosystem that covers the whole country. Okay, I think that that's basically the idea that has to be exported into the different countries in Europe to create this supply demand with the supply chain that you require that not only allows for proving that the technology is there and is available and is safe to use, and it is cost effective, but also that creates this innovation cluster that you require to basically do things like what we are doing in animal, that is to discover innovative technologies to basically scale up these systems in a much better way as well.
Yeah, I think it's very interesting when you bring up the examples of Ireland and then the examples in other islands like Mallorca, because it brings up the importance of access to clean water and using seawater in an intelligent way so you can use it for other resources like the production of hydrogen and then the interconnection of systems and the interconnection of ecosystems. I think that's probably also the idea of the European Union to basically have a whole continent, not only the islands, that is reliant on the hydrogen economy. So that's a very interesting point. We do have another question from Michelle Prestad, who's an expert in corrosion, but again, it does feel very technical. So I think it's probably better if we just follow up on an email later on. I can put you in touch because that's probably the easy solution. And then we have another question from Alberto asking about the slides. So this is a great opportunity for me to remind you that the whole webinar will stay published here on YouTube. So it was streamed live, but it will remain as a free video in the Animal channel, where you can also find a couple of other videos about Animal. So I think with that, I can just thank Pau again for the great presentation and his time talking about direct seawater electrolysis. Thank you so much, Pau. And
Thank you, Fernando.
yeah, before before we go, I just want to remind everybody that this is just the beginning of a very exciting series of webinars, not only about animal and direct seawater electrolysis, where we'll get to meet our partners and we get to meet the different people working in animal, but we will also get to talk to other people in the hydrogen portfolio of the European Innovation Council, as well as people from industry, people from policy, and many different interesting voices in the world of green hydrogen and electrolysis. So if you're interested in knowing more about AniMail or about the webinars, please do subscribe to our newsletter. You're gonna have the link in the chat. And then also, if you're interested in learning about any of the aspects that were mentioned during the webinar, like the use of more abundant materials for catalysis, the use of non-fluorinated membranes, the different types of hydrogen that are available, maybe go to our website. It's animal.eu. So maybe go to our website and check out the different blog posts, the different materials we have, and yeah, explore a little bit to see what Animal has to offer. It was a true pleasure hosting this webinar, and I really look forward to the next one. It will most likely be at the end of April, but please do subscribe to our newsletter to learn more about the date and the time. And thank you everybody for joining. It's been a great pleasure having you all connected. And yeah, I look forward to the next webinar in the series. Stay tuned for that. Thank you for joining.